Trig Max Min Problems. All right, so we've actually done max and min problems in a previous unit. Now we're just going to be applying situations where, well, we have to deal with trigonometry expressions. This will look similar to physics. We've done a lot of this in Physics 20 if you've taken that. So some of the concepts there will kind of help if you can remember way back to Physics 20 there. So let's jump into the first one. In the physics experiment, a student attaches a weight to a spring, then stretches and releases the spring and watches the weight bounce up and down. The height of the weight above the table in centimeters as a function of time in seconds can be modeled by the function h of t is equal to negative 15 cos 4.2 t plus 17.5. Find the maximum and minimum height of the weight as it bounces on the spring. So we use derivatives to do this, but then you can check using what we know about sinusoidal functions. Okay, so very first thing, I'm just going to write down that equation again. So this would be h of t is equal to negative 15 cos 4.2 t plus 17.5. Now let's think about what we're looking at. So with this spring mass system. Right, so this spring would be oscillating up and then down, up and then down, up and then down. So what's going to be helpful is to think about the speed at any given point on this graph. So in this graph, like when this thing is bouncing up and down, when it gets to a point where it's at the top, let's say, the question is, how fast is it going? Well, it has to be going 0 before it comes back down, right? The velocity there has to be 0. And then you've got the same situation when the spring is stretched all the way to the bottom. Again, it's got to be going 0 centimeters per second before it goes back up again. So there's going to be that pause. Okay, so that's our first hint, where we should be thinking about this thing in terms of speed. Is there any way we can change this expression in terms of height into speed? Well, yeah, that's going to be taking the first derivative. So if we take the first derivative, then we'll now have an expression for the speed of the system. So let's do that. We'll say here, and I'll make some different colors. H prime of t is equal to negative 15 times negative sine of 4.2 t, and then times the derivative of the inside, right? So then that's going to be times 4.2. Okay, so just simplifying that up a little bit, the two negatives become positive, and then the 15 and the 4.2 would become 63 sine 4.2 t. So there you go. There's h prime, which could also be written as v in this case. So what would we do next? Well, if I want to figure out the times where we're either at the max or the min, I wouldn't really know which one yet, but what we should do there is just set the velocity or the first derivative equal to 0. So if we do that, so just write that again, 63 sine of 4.2 t. Okay, now I can divide both sides by 63 if I like, which would just make this sine 4.2 t. Now, this is why we had to do some review for Math 30-1 concepts. This is a double angle, isn't it? Which isn't that bad. All we're going to do is just kind of pretend for a second that this is one angle. Okay, just forget about the 4.2. Just call that theta if you like, for now. So what would that be equal to? Like, what would 4.2 t be equal to? Put it on the other side. Well, it's whatever sine theta is when it's equal to 0, right? So an angle of 0 degrees would be, you can picture that unit circle in your mind. The height on the y would be 0. Okay, so it happened there. It would also happen at pi. Right, you go 180 degrees around, you have a height of 0 again, right? Your sine value is 0. And then again at 2 pi, and so on. So those are the values that this is equal to, this both together. I just want t, so what's left to do is just divide everything by 4.2. So our times would be at 0 over 4.2, which is just 0. It would be at pi over 4.2 and 2 pi over 4.2. Now the decimals, I'll leave them like that for now, but at the end we'll clean those up if we rewrite them again. But yeah, so now just think about this, like I've given you 3 different ones. This would actually keep going, right? Because it's oscillating up and down. So I could actually choose. I could choose 0 and pi, or I could choose 2 pi and the next one over, because really I know that one would be my max and then the next one would be my min. The problem is right now I just don't know which one's which. I don't know if this is my max and this is my min, or if this is my min and this is my max, right? So I need to figure that part out now. Okay, so let's sketch out a quick number line with 2 of our critical numbers there. I'm going to choose the second one and the last one there. Oh, and this is 0 over 2. That's just 0. You can write that as 0 if you like. But okay. So then let's write that. So that's pi over 4.2 is our first one. And then the next one would be at pi over, 2 pi over 4.2. Now what I'm after is really figuring out on that number line, like would this be a max or would it be a min at that point for each of them? Now you could do it 2 ways, like there's different ways to do this now, right? We could throw in some test values, anything to the left here, anything to the right. We could figure, okay, if this thing was increasing and then throw it into the first derivative, right? So if we get a positive value, that means we'd have a positive slope. And then on the next one, if it was decreasing, then okay, then this would definitely be a max, right? If that was the case. And then so on. So you could do that with the first derivative. You know what? The other one we can do, though, is we could figure out the second derivative, right? Because if I throw in, let's say, this point and this point into the second derivative, well, let's just do it. I'll show you what we're doing. So here, for a second, I'm going to write down, well, let's find the second derivative. So the first derivative was, here, change color again. The first derivative was h prime, I'll make it red still, h prime of t was equal to 63. There, I gotta give myself some room, sorry guys. H prime of t is equal to 63 sine of 4.2t. Okay. So now let's take the second derivative. So the second derivative, double prime of t, is 63, and then the derivative of sine is cos. So cos 4.2t, and then times the derivative of the inside. So times 4.2. All right, so let's think about what we just found there. The second derivative. Okay, so the first derivative was height, the second derivative was velocity, the equation was height, the first derivative was velocity. The second derivative would be my acceleration. So this is really going to tell me if my acceleration is downward or whether my acceleration is upward, right? Which is also just going to tell me whether this thing is concave down or concave up. So what I'm going to do now is I'm just going to throw these critical values into my second derivative, right? So let's just write this. We'll write h double prime of t, okay, for these points. So at pi over 4.2, well, if I threw in for t, pi over 4.2, that would just be pi, right? Because 4.2 would cancel with 4.2. So cos of pi would be -1. So that means this thing's coming out negative. So that means I know that this is negative at that point. Okay? And I also know it's either a max or a min. So what does that mean? Well, that means that I know that h of t must be opening down, right? Because if it's negative, it'd be opening down like that. There you go. So that must be a max. All right. Let's do the next one. So if I threw in 2 pi over 4.2, then that would really be saying taking cos of, well, the 4.2's again would cancel. That'd be like cos of 2 pi, which would just be 1, and positive 1. So that's going to be coming out positive. So what does that mean? Well, that means that this thing is going to be opening up. So that must be a min. And there you go. That's kind of everything we need. So we have a max at pi over 4.2, and we have a min at 2 pi over 4.2. Now, that's weird, I wrote theta. Now, okay, so that's good enough. You could typically write it like this, but the decimals are a little bit awkward there. We probably should have wrote that as, well, multiply the bottom and the top by 10 first, right? So that's 10 over 42. So then 5 over 21. So 5 pi over 21. Probably would have been a better way to write that. And then for this one, this would have been, so times 10, so 20 over 42. So that would be 10 pi over 21. Sorry, no. Yeah, 10 pi over 21. So that probably would have been a better way to write that. So now it's confusing you. Maybe erase those. Okay. Okay, find the maximum and minimum velocities of the weight and the times at which they occur in the first period. All right, maximum, minimum velocities. Maybe you're figuring out where to go here, but just to get my bearings, let's write down the equation I found for velocity, right? The first derivative. So that was v is equal to 63 sine 4.2t. Now, okay, so now the maximum and the minimum velocities. So where is that going to happen? If we look back to this, right? So you could imagine as this thing was oscillating back and forth, it would happen right in the middle, right? It goes from having 0 velocity, and then right in the middle, it's got its max velocity, and then min, and then and then 0, and then 0, and then max again as it goes back up. So now thinking in terms of physics, what would the acceleration be right in the middle? Well, it would be 0, wouldn't it? Right? So like because it's in the middle between, well, at the top here, like if you remember back to physics 20, the acceleration is downward, and in the bottom the acceleration is upward. So right in the middle, you're in this sweet spot where the acceleration is neither down nor up. It's nothing. It's come to it's 0 at that point. So even though you're at your maximum speed, you have an acceleration of 0, right? That can happen if you remember back to your grade 11 physics. So okay, so that's in terms of physics. Now in terms of math 31 or calculus, this would also be an inflection point. Right? So this would be a point where this thing was, like if we were drawing our, it was going up and down, right? It would be the point right where it changes, right? So it changes from a max, it's concave down to concave up, right in that inflection point. Well, if we remember back, that's where the second derivative is equal to 0. Okay, so let's look at that. So the second derivative is equal to 0. So that's what I really need. I got to figure out the second derivative, which I already did in the last question. Yeah, so let's write out the second derivative. So the second derivative, so h double prime of t is equal to, and it was this, right? 63, and then there was 4. I never did multiply those, so let's multiply those now. That would be 264.6 cos 4.2t. Okay, so now remember what I'm looking at here. This really is also an expression for the acceleration. And I want to know where the acceleration is equal to 0, or where the inflection point is. So in this case, if I want to figure out max speeds, I'm going to set my second derivative equal to 0. Okay, so this 264.6, I can divide that out, so I just get cos 4.2t. So where is cos equal to 0? Well, so cos is equal to 0 at pi over 2 and 3 pi over 2. Right? So remember, we're treating this like just theta for now. It's just like one thing. So we'll say 4.2t, or theta, is equal to, and then it'd be pi over 2, and then 3 pi over 2. And just for a minute, just check that this makes sense. This does make sense, doesn't it? Because last time it was 0 and pi, right? Those were where our velocities were 0. And now these are halfway in between, isn't it? Pi over 2 is halfway between these. That makes sense, right? That's going to be, you have your maximum speed halfway between your maximum and your minimum. All right, so this is all looking good. So now we'll say t is equal to, and then that'd be pi over, let's write like this, 4.2 times 2 for a second, right? I'm just dividing everything by 4.2. And then 3 pi over 4.2 times 2. Now simplify that up a bit. I'm going to multiply the bottom and the top by 10. So then that'd be like 10. That'd be turned into 42. And then the 10 and the 2 will turn to a 5. So that'd be 5 pi over 42, comma. And then same little trick. So it'd be 30 pi over 42 times 2, right? Just multiply the top and bottom by 10. So then that would be 15 pi, just the 30 and the 2, over 42. And then that would simplify to 5 pi over 14. All right, and that was 5 pi over 42. Okay, so we just found where these occur, right? The times that this is going to happen. So now we actually have to figure out the velocity, though, like how fast was it actually going. So, okay, I have an expression for that. That is v, or here I'll write it as h prime, first derivative, is equal to 63 times sine 4.2t. So then we'll input our values there. So h of 5 pi over 42, h prime, is equal to 63 times sine 4.2, and then this is where I'll input that. So 5 pi over 42, and that gives you 63. So 63 centimeters per second. Okay, and if you input 5 pi over 14, you get negative 63 centimeters per second. Okay, next one. Find the maximum perimeter of a right triangle with hypotenuse 20 centimeters. Give the answer as an exact value. So let's draw out a picture of a triangle. Oop. Right, and we'll call this y. Come on. And this x. And then we know that the hypotenuse is 20. Okay, so where we'll start with this, let's consider this the angle, and then we'll make an expression for x and y. Okay, these are going to be really our constraints. So we can say cos theta is equal to x over y, or sorry, x over the hypotenuse there, so x over 20, and sine theta is going to be y over 20. So rewriting those just as an expression for x and y, we'd say x is equal to 20 cos theta, and y is equal to 20 sine theta. Okay, we're going to use those in a second. So now that we have those constraints, right, like this has to be the case. right, for whatever whatever we end up doing from here. So now if we want to find the maximum perimeter, then let's make an expression for the perimeter of this. So that would just be x plus y plus 20 is equal to the perimeter. So actually, let's write perimeter on this side. So the perimeter is equal to. All right, so now picture what's happening here, right? There, you can picture the y and the x changing size. So the y would be bigger, the x would be smaller, the x would be bigger, the y would be smaller. In the end, you're going to get a picture of something, right? So this is perimeter, and this is, let's say, our value for x or y. Then we're going to come to a peak, right, at the top, and that's what we're after. We want to figure out the maximum perimeter. So really, I'd like to figure out where the slope is 0, so the first derivative. So that's what we'll do. We'll say p prime, or the first derivative. Ooh, actually, one more step. Got ahead of myself there. So let's rewrite an expression for this, though. So we'd say p is equal to, and then instead of x's and y's, let's throw in our constraints, right? Because these are actually both in the same variable as well, right? They're both in terms of the angle. So that'll be good. So x was actually sine, or 20 cos theta. Y was 20 sine theta. And then plus 20. So now we'll take the first derivative. So this would be 20, and then instead of cos theta, this is going to be negative sine theta. And then 20, and then instead of sine theta, this is cos theta. And then plus 0, because I'll just leave that last part out. So this would be negative 20 sine theta plus 20 cos theta. So now I'm going to factor out either negative 20 or 20. I'll factor out negative 20 sine theta minus cos theta. All right, and now that's a pretty good way to write it. So I think we're pretty set up. And now what we want to do there is we want to set that equal to 0, right? Because I wanted that slope to be 0 at the top. So I'll divide both sides by negative 20. So this is really 0 is equal to sine theta minus cos theta. So sine theta is equal to cos theta. Now from there you could say, okay, where is sine theta equal to cos theta? Well, they're both equal to root 2 over 2 at pi over 4. So you could do that, or you could rewrite this as tan, right? Because I could say, you know, sine over cos is tan, so I could say divide by cos on both sides. So we'd have tan theta is equal to 1. So where is tan theta equal to 1? Well, same thing, it's pi over 4. So theta would be at pi over 4. Now remember to think about the context of the question. You might say, yeah, but it's also at 5 pi over 4, but that wouldn't make any sense, would it? It would make sense for that to be 4 pi, or pi over 4, but not 5 pi over 4. That'd be an obtuse angle. So, okay, so there you go. Now, what's left to do next is just put it back into into the perimeter equation. So I'm really looking up to here, and we're just going to be throwing in pi over 4 there. So the perimeter would be 20 times, and then cos pi over 4 is root 2 over 2, or 1 over root 2. We'll write it as root 2 over 2. So root 2 over 2. And then plus 20 times root 2 over 2. And then plus 20. Okay, now I'll just simplify the 20 and the 2 in both of those. So that'd be 10 root 2. plus 10 root 2 plus 20, and then just combine my like terms, so that would be 20 root 2 plus 20.